Welcome. This is Chapter 4, Section 3, Logarithmic Functions. So logarithmic functions have applications in real life. Something that logarithms do is they're used to measure earthquakes using the Richter scale. And this is a link to a video on the Richter scale. And you'll notice the Richter scale increases rapidly. So there's quite a bit of difference between each consecutive level. Now, so when we use the Richter scale, it's actually a base 10 logarithmic scale. So it can be represented by y equals 10 to the x, and we'll have a look at that. So when we're comparing magnitudes of earthquakes, we have to convert them. So here's a reason why. So suppose we're measuring two earthquakes and one is 700 times more powerful than the other. This can be represented as 10x equals 700. So what happens when we try to solve this? Let's have a look. 10x equals 700. I could, well, I can't really use any of the algebra we know to do this. So it cannot be solved using the basic algebra that we're all used to and that we all love. And what that means is that if I say I had 10 times x equals 700, well, I could obviously solve for this because I could just divide by 10. But I can't do that because it's a power. And you may be thinking, oh, Miss Harding, what about the root? Well, I can take the xth root of 10x, 700. This becomes 10 equals the x root of 700. But now we still have an x to deal with. And I mean, there's really no way we have of solving that. So we're not going to be able to use basic algebra, and that's a huge problem. So there's ways that we could solve this. We could estimate it, so we could plug values in. Well, notice that 10 to the 1, or we'll do 10 squared, that's 100. 10 to the third power is 1,000. So 700 is obviously somewhere between 10 squared and 10 cubed. Well, the problem with using this method to estimate x is that it's time consuming, and you probably will never get the correct answer down to the decimal point. Now, using a graph. Well, we could use a graph, but as everyone knows with a graph, it's imprecise. So what that means is that if we're using a graph, the values won't be exact because we do have to estimate based off of what the graph looks like. So it might look like 2, but it might really be 2.00001. And eventually you would, depending on how many calculations you do, how big the numbers are, you could get a wrong answer. And logs are used a lot in business school, so it's really important that we don't usually round until the very, very final answer, because we're talking about money here. So let's see. So let's say this is our graph of an exponential. We'll call this 10x equals y. So what do we see here? Of course, one thing is that horizontal line test. Horizontal line test is always passed. So I could draw a line anywhere on here. And what does that mean? That means it's 1 to 1. So let's look at a flow chart here. So we have y passes the horizontal line test, and because y passes the horizontal line test, we can say that y is 1 to 1. And because y is 1 to 1, we can say that we know y has an inverse, because that's the whole point of the horizontal line test. So we know y has an inverse. So it just so happens that the logarithmic function is the inverse of an exponential. So this would look like exponential, the f inverse is a log. So that means the inverse of a log is an exponential, and they just kind of go in a circle like that. Now, what is a logarithmic function? This is our logarithmic function. Y equals log bx. So one way we can say this is b raised to the power of y is x. So if we had, let me get a pen. Again, it's so hard to switch between these two. Mid-video at least. So if we have an exponential, that's going to look like y equals b to the x. But the logarithm is y equals log b x. So that we will get b to the x equals y. Now, how do we solve these? Well, what this says is that we need an exponent, and we're going to look here for an example. Log 2, 32. So we need an exponent x such that log 2 equals 32. And what that means is 2x, 2 to the x, is going to equal 32. So one thing we can certainly do, and we can rearrange this. So if we have y equals log 2, 32, then that would be 2 to the y equals 32. Sometimes it uses x a lot interchangeably because it's an inverse, and sometimes you will see it like this, using x. And it just is the same process. So here you can see we just kind of plugged in values, and if it's small enough and it will go in without any decimals or fractions, that's generally a pretty easy way to do it. So this means that log 2, 32 is 5. So you would say log base 2 of 32 is 5, and that little 2 is that base. So log is a calculator button, so it will be on your calculator. So one way that we will go back and forth is if we have y equals b to the x, then we are going to have b to the y equals x. So b has to be greater than 0, and it cannot be equal to 1. So we cannot take a negative logarithm. So what that means here is that log, this has to be positive, this base. It makes no sense to say log -3. with a base -3. That doesn't make any sense. It cannot equal 1. We would get more or less some type of constant function, which is not an exponential. And also x has got to be greater than 0. So once again, you cannot take a negative logarithm. So if I had log base 2 -4, that's not going to work. Actually, wow, I kind of just rewrote the same thing, didn't I? I didn't even notice that. This is one of the bad things about not being in class, is you guys can't point out my mistakes. So if we had by equals x, we would have y equals log b x. There we go. So the bases have to be greater than 0, the bases cannot equal 1, and our x value has to be greater than 0. So why do these conditions exist? So x is greater than 0, so log cannot be taken of a negative number. And I'm sure there's a much more eloquent way of saying that. Log cannot be taken of a negative number. So why does b have to be greater than 0? Well, the base can't be negative. Or else we would have an oscillating function. It would have a lot of back and forth between positive and negative, and we can't have that because this is the inverse of an exponential. So, like for example, if we had -1 to the y equals x, we would go between, when y equals 0, we would go between 1 and -1. So it would just go back and forth between -1. So we would have a graph that looks something like this. Not 1 to 1, so it wouldn't have an inverse. So all of the rules of logarithms would start breaking down here. So our b cannot equal 1. That's because 1 to the y equals x is just 1. So it's a constant function. F of x equals 1. And you would, and that would absolutely fail the horizontal line test because it is a horizontal line. Using common logarithms. So a common logarithm, if you ever see a logarithm written like this, log x equals y, then you understand that it has a base 10. Is that how I wrote it above? I want to be sure to stay consistent. Yes. So it's a common logarithm, and it's what you will see on your calculator when it just has log. They're used in the Richter scale. They measure star brightness. pH, for any of you that have an aquarium, pH is measured in logs. It's always understood here that the base is 10 because that's easiest to deal with. So this changes what we have to 10 to the x, and we're going to say 10 to the y equals x, which gives us log 10 to the x equals y. Yes. And you would just normally see this written as log x equals y. So the base e, it is the most used base. So especially in the sciences, which is why we cover it, these are called natural logarithms. And you will see them as ln x equals y. So ln is how you would see this. So if we have e to the y equals x, then we're going to have ln x equals y. And note we also need x is greater than 0 here. Can't take a negative logarithm. It exists for the same reasons above. So what does this mean? So what this means is that now these two are inverse functions. So that means ln x equals y is the inverse of e to the y equals x, and vice versa. So they go back and forth just like logs do. We will go over examples in class on how to solve these things. And this is pretty much logarithmic functions. So thank you for joining me, and I look forward to seeing you in the next one.